Alright, this is lesson 36 for 7th grade, and today we're talking about ratio and sample space. And these two things together will help us lead into probability, which we have seen before, but as always, we will get more into it as the year goes on, and as we progress to high school and college, things like that. Alright, so here's what we want to accomplish today. We want to define what a ratio is, and that's probably a review, but ratio is a big part of math, and we're going to drive the point home of ratio pretty hard this year and into the years to come. Oh, sorry. We also want to use these ratios to help us solve problems. We'll be doing this more so later on, but we're going to sort of get into it today. And we're going to want to be able to identify the three numbers involved with ratios. Usually in every ratio there are three numbers that are pretty important to help us solve these types of problems. And lastly, we want to relate the sample space to ratio and probability. And we'll get into what that is in a second. So, to start off, we have this big slide here explaining what a ratio is and all the different ways that we can express a ratio. Start up here. A ratio is a way to describe a relationship between two numbers. So ratio is in between two numbers and we're relating them somehow. So for example, if there are 12 boys and 16 girls in the classroom, the ratio of boys to girls is 12 to 16. And then it gives us a bunch of different ways that we can write that ratio. So one way that we can write the ratio is as a fraction. So we can write 12 to 16 as 12 over 16, and we know that 12/16 reduces to 3/4. If we divide each, the numerator and the denominator by 4, 12 divided by 4 gives you 3, 16 divided by 4 gives you 4, so it reduces to 3/4. So now we have our ratio of 3 to 4, and that can be written in the following different forms. So we can use the word 2, 3 to 4. The ratio can be written as a fraction, 3 over 4, or 3/4. We can write the ratio as a decimal number. So 3 divided by 4 gives you 0.75. Or we can use it with a colon, 3 to 4. So where the colon is, we would still say 3 to 4. But these are all acceptable ways to write that different ratio. And here we have the numbers used to express a ratio are stated in the same order as the item's name. If the boy-girl ratio is 3 to 4, then the girl-boy ratio is 4 to 3. Order does matter, basically, is what they're saying here. So if it says boy to girl ratio, we want to make sure we line up the boy's number and the girl's number in the right order. So we can see here, boy to girl, 3 to 4. Girl to boy, then would be 4 to 3. And lastly, although we may reduce ratios, we do not express them as mixed numbers. So 4 to 3 or 4 over 3, we would not change that to a mixed number in that case if we left it as a fraction. Alright, now here are the three numbers that we were talking about here. So it says most ratios involve three numbers, even though only two numbers may be stated. So when we were talking about the ratio of boys to girls is 3 to 4, the unstated number is 7, and that represents the total. So 3 plus 4 gives you 7. And my question is, does this mean that the total number of boys and girls is 7? So remember, and our answer here would be no. Because remember, the total amount of boys was 12, and the total amount of girls was 16. So if we add those together, there are actually 28 total students in the classroom, but we ended up reducing. So this is our ratio total, but it's not our actual total. Our actual total was 28 students. So just remember that does not mean you have 7 students in the classroom, but it is your ratio total, which will help us out later on in solving those problems that I was talking about. Alright, so let's try a problem here. In a class of 28 students, there are 12 boys. What is the boy-girl ratio? So we want boys to girls, and let's go ahead and just use a colon here. So we have a class of 28 students. This is a total right here. This is our overall total, and then we were given 12 boys. So in order to figure out how many girls there are, we will do 28 minus 12. We should get our girls. 8 minus 2 is 6, 2 minus 1 is 1, and we get 16. So we get a ratio of 12 boys to 16 girls, and we can reduce that. We would say, let's see, we could divide each of them by 4. So if we divide 12 by 4, we get 3. 16 divided by 4, we get 4. So there's your 3 to 4. So it looks like the same problem that we just solved before, except for now, or the problem they were talking about right here. But this is how we would solve for it in this format. And then it just switches it around and says, what is the girl-boy ratio? Well, that just takes this, and we're going to switch our order from 4 to 3. And remember, you can write it in all those different formats, fraction, decimal, doesn't matter to me. Okay. So then I have a couple examples that we will go over. This would be one of them. It says the team won 4/7 of its games and lost the rest. What was the team's win-loss ratio? Okay, so won 4 games. We need to figure out how many they lost. Did they lose 7? No, they played a total of 7 games, or at least in the ratio format we know that they won, or they played 7. This doesn't mean that they played 7 games. It does mean that whatever fraction there was, it could have, so let's say they won 16 games total. That would be 4 times 4 and 7 times 4. So they could have played 28 games total. We're not sure what they played. All I know is that this reduces to 4/7, and I know that when we're talking in the ratio form, this is the total right here. So we do know that as far as the ratio goes, 7 minus 4 gives us 3. So this means that of this fraction, they should have lost 3 games. So they won 4/7 of their games, they lost 3/7 of their games. So what was the team's win-loss ratio? Well, we want wins to losses. So win and lose. 4 to 3. So we should be looking at this one right here. And just want to point out, remember that this does not mean they just played 7 games. They could have played whatever, as long as this ratio stands true. All right. I'm gonna check my time. All right. Here's another one. There are red marbles and green marbles in a bag. If the ratio of red to green marbles is 2 to 5, what fraction of the total number of marbles is red? Sounds kind of confusing. So now we want to look for what fraction of the total number of marbles is red. What fraction of the total number? Okay. So we know that we have a ratio of 2 to 5. So we've got red to green. So let's do this. So red is 2 and green is 5. So a ratio of 2 to 5 there. We want to figure out what fraction of the total number of marbles is red. So we're going to take our 2, which is red, and we're going to put that over our total number as far as our ratio goes. So our total number then would be 2 plus 5, or 2 plus 5 here. So 2/7 would be our fraction of the total there. So 2/7 of those marbles should be red. And this makes sense because then 5/7 2/7 would be red. I'll say 2/7 are red, and 5/7 are green. Okay, so we don't know how many marbles are in that bag total, but we do know that of the total, 2/7 are red, and then 5/7 should be green. It's a little confusing at first, but it's not too bad once you think about it a little bit. Alright, so we have talked about probability as a fraction. We can also express probability as a ratio, because probability involves part-total relationships. So basically this is our format for probability. We have some sort of event, so the probability of an event is the number of favorable outcomes over the total number of possible outcomes. Okay? So this will help us introduce sample space. It says the probability experiments we have considered so far had outcomes that were easy to count. Many probability experiments have outcomes that are more difficult to count. To help us count outcomes, it is often helpful to list the possible outcomes of a probability experiment. The list of all possible outcomes is called the sample space. So the total number of outcomes for an event occurring is called the sample space, and that's going to help us find probabilities of certain events. So for instance, what is the sample space for the following experiments? Well, if you flip a coin once, how many different outcomes are you going to have? You're going to have 2. And we want to be very distinct, and we want to show what those outcomes are. So we use those little brackets there. You're either going to get a heads or you're going to get a tails. So we write H. That would be your sample space for flipping a coin one time. Alright, if we roll a number cube once, we're going to use our brackets again. This is the official way to write a sample space. Rolling a number cube once. A number cube has 6 numbers on it. You can get a 1, a 2, a 3, a 4, a 5, or a 6. Okay? So that would be your sample space, the list of all the possible outcomes that you could get. Picking one letter from the alphabet. That's going to have 26 outcomes. A, B, C, all the way to Z. And I believe my next, yeah, I do have these listed here. So you can see that, like I did, they have them all in brackets here. Heads, tails, 1, 2, 3, 4, 5, 6, and all of the possible letters that you could get. We're getting close on time here. Might have to turn this one into 2 parts today. Alright, so first thing here with this example, says a coin is flipped and the spinner is spun. What is the sample space for one coin toss and 1 spin? Alright, and what is the probability of heads and a number greater than 2? So, I might go ahead and just stop here and throw this on part 2 of the video, so stay tuned.